So the second Winton Capital Award now for geophysics is given by Dali of the University of Exeter, and the title is The Mysterious Interior of Jupiter and NASA's Juno Mission.
Yeah, okay. Thanks very much. I feel very honored to give a talk here in the Royal Astronomical Society, and thanks for giving me this award. And today I want to introduce you to all of you about Jupiter and this latest news of the Juno mission. Oh, okay. There's mainly 4 parts of this talk, and firstly, in the first part here, I want to bring all your attention to a few impressive facts of Jupiter. And the second, I want to discuss something which, why and what aspects we still don't know very well about the interior of Jupiter. And the third, I want to introduce what Juno is going to do to help us to improve our understanding of Jupiter. But even though we have the observations, but we have to make a lot of efforts to interpret the data and really turn the observations into knowledge. So that's in my 4th part. Okay, and this first picture is the comparisons of all these 8 major planets in our solar system. And the first impression of Jupiter mass is outstanding, right? So the first fact comes to us, Jupiter is very big. And in terms of diameter, and it is an order of magnitude larger than our Earth. And also Jupiter has an extraordinarily strong magnetic field. It's possibly the strongest in the solar system. Not possibly, it is. And the magnetic moment is nearly 20,000 times higher than Earth. And another very fascinating feature of Jupiter is the winds on its atmosphere, in its atmosphere. And we know this, if you look at Jupiter, we know this feature we all can observe, and it's the belt and zones on the Jupiter's atmosphere. And they actually represent strong jet winds or zonal winds in the atmosphere. And these winds are very strong, and a typical speed in the equatorial region could exceed 100 meters per second. And an important feature is it's strong. It's not only strong, but also very stable. It lasts for a few centuries since we started to observe it, and it doesn't change too much. And also you see this major big vortices, like this is the great red spot. Its size is it's about an Earth size. It's tremendous, and it's fierce. The wind speed is strong. And also, the same thing is quite interesting is, not like the typhoon or hurricane on the Earth, which last only a few days. And in Jupiter's atmosphere, and this kind of big red spot, and also last a few centuries. And that's the question, and why we have such strong and stable winds. And the 4th fact of Jupiter is about the interior. And if you don't like the boring science, then you can look at this cake. And it's a mud cake, an almond butter cake, and a vanilla sponge. And it's respectively correspond to the inner core and the metallic hydrogen layer and the molecular hydrogen envelope. This is a schematics, of course, and about this cake, apart from this relative scale of the thickness of the layers, and actually to represent quite precisely the inner structure of Jupiter. And overall speaking, Jupiter is a large gaseous planet revolving around the Sun, and at its orbit distance to the Sun is about 5 astronomical units. The 1 astronomical unit is the mean distance from the Earth to the Sun. So it's about 5 AU, its orbit. And it has a strong wind in the atmosphere, and it also has very active flows and action, all these flow motions in the interior, and generate a powerful magnetic field. And it emits more energy than it receives from the Sun. So the interior of Jupiter is very active. Then why Jupiter is important? That's twofold. First, Jupiter is an outstanding member in our solar system. So it's crucial for us to understand Jupiter. And via this research into Jupiter, and we can understand a lot of planetary physics. And second, Jupiter represents a large category of exoplanets. And so far we have discovered more than 3,000 exoplanets, and most of them are gaseous. So if you understand Jupiter well, you can infer or guess what's going on in the exoplanets. It helps us to understand exoplanets. So this is the 2 reasons why we need to study Jupiter and understand it. Okay, now we have a few puzzles, and as in my title, it's a mysterious interior of Jupiter. And why it is mysterious? First, we don't really know its interior structures, although we have already made cake out of that. We know roughly there should be these layers, an inner core, a metallic region, molecular region. But because we don't understand quite details of the compositions and equation of state, and we can't derive its structure and equilibrium figure very well so far. And we are lacking of observational data. We can't constrain our model very well. And we don't know the inner core and what its size, and does it exist or not, and what is the composition of the core. And second is, this perhaps is one of the most important reasons why NASA sent a Juno spacecraft. And I said the wind on the Jupiter is different from the wind on our Earth. It's strong and stable. The most important thing is why they are stable. And it could be like its driving mechanism of the wind could be like the Earth, like the weather. And it's because of the temperature difference, and it can drive this global circulations. But for Jupiter, it's a bit different because the Jupiter is not like the Earth, it's gaseous. And there's no clear boundary to divide the atmosphere from the interior, right? And actually, Jupiter, from the outside to the most interiors, that's continuous. Everything's transitional, not a clear-cut boundary. So it's hard to imagine if you have a wind and a thin layer of wind on top of a stable stratified layer. That's not quite understandable. And if you have a thin layer of wind and it can't exist there stably. So there is some theory, say it's deep. The wind is driven by the deep motions of fluids. And this deep flow actually penetrates to the top of the Jupiter and control the pattern of the wind on the top of the atmosphere. So Juno mission wants to help to answer this question. Is the wind deep or shallow? And third question is about magnetic field, and we still don't know how exactly. We have some ideas, a general principle how magnetic field is generated, but we still don't know precisely how this mechanism called dynamo works for Jupiter. Then now let's turn to the Juno. This is the Juno spacecraft, and it was launched in 2011 and arrived last year. And now it's in the orbit, it's doing measurements. And this photo just give you an impression and how large this spacecraft is. This is one of the 3 panels. Oh, this figure doesn't look all right. It doesn't matter. And how it doesn't looks like what it is in the computer. Anyway, you have Jupiter, and how a spacecraft can help you to understand the interior. That's because of gravity and all the mass distributions and all the disturbances in the interiors. You can't see it, but it will be reflected in the external gravity field. So if you send a spacecraft there, and the spacecraft's orbit will exactly give you the information of all these interior signals. But this is the principle, and how to interpret the observations and get this data out. That's what our researchers need to do. And Juno's observations brings a few challenges. First, its measurement is unprecedentedly accurate. Not like previous, before Juno, there were a few spacecrafts, and either fly by like Pioneer or Voyage, and or Cassini-Huygens, and they fly by Jupiter. They provide some orbital segments which could be used to deduce the Jupiter's gravity. And like Galileo is Galileo is mainly study Jupiter, but it also paid a lot of visits to its satellites, not really solely circling the Jupiter. And Juno is different. Juno is devoted to Jupiter, and it enters the polar orbits of Jupiter and will complete its mission on these polar orbits. So Juno's measurement of the Jupiter's gravity will be extremely high. And this is a challenge because you have very accurate observations. Then all your models, your methods, your interpretations are highly demanded. And Juno's measurement, we say it measures gravity, but gravity itself will not tell you anything because it's a comprehensive signal. It contains all the disturbances. It contains the information from the equilibrium large-scale structure. It also contains the signals from all the small-scale interior flows. So as a researcher, you are responsible to do a model and to distinguish between them. And third, Jupiter is rotating very fast. Our Earth the rotation period is 24 hours, we know, and Jupiter is much faster than that. And the faster rotation means the shape distortion from the spherical geometry is much larger. And Jupiter is a gaseous planet, not like Earth. Earth is a rocky, so it's denser, and it's rotating slower. So it's more or less a sphere. But Jupiter is less dense, and it's rotating extremely fast, so it's very oblate. Not oblate, and sometimes irregular. And dynamos, that's related to the magnetic field. And we say inside of the metallic region, and dynamo processes is going on. And the dynamo process is non-axisymmetric, which so far we still don't have. We don't have models we don't have tools to model this kind of non-axisymmetric flows. These four are challenges brought about by Juno. So now it's our contribution and our efforts to interpret Juno's observations. Firstly, we have two models. That's for the first time at the left, we say the three-dimensional self-consistent multi-layered model of Jupiter. Our model has this layers structure, the molecular, metallic, and in the core. And in the molecular region, that's the zonal wind. That's what you saw on the surface. There's a belt and zones. And it represents the flow structure like this, columns. This is a cross-section in the meridian plane. And if you rotate it, so it's cylindrical. So wind exists in the molecular region and in the metallic region, and we have these dynamo processes. The dynamo processes, as I said in the previous slide, is non-axisymmetric, but zonal winds are axisymmetric. And we have it in the core. That's the mud cake. What I want to address here is, if you look at the shape, it's a bit exaggerated, but I want to draw your attention is the shape of Jupiter and all these fast rotation planets is irregular. They are not perfectly, not in your mind, you may think it's oblate, so it's a spheroid. But actually, from theory, we can prove generally they are not spheroidal. And especially when your rotation is fast, this kind of departure from the spheroid, it becomes very important. If you don't take them into account, you can't interpret such high accurate data obtained by like Juno mission. So these two are our models. And we use this model to predict the observation. And if we have observation, we can use this model to do inverse. Then we can determine interesting parameters like what is the size of the core and what is the mass of the core and how thick this metallic region is, how thick is this molecular envelope is, and how fast this kind of non-axisymmetric dynamo motion is. And all this important informations can be deduced from observations. But if you don't have these models, you can't achieve that. This is our method. We use three-dimensional finite element method. We discretize any computational domain by tetrahedrons. And typically, in one calculation, we could use a few million tetrahedrons. And this is one of our expectations of the observations. And okay, let me explain a bit. This figure presents called gravitational coefficients, which is the coefficients reflect the structure of the external gravity field measured by the spacecraft. And the lower order means large scale structure of the gravity field, and the higher order means the small scale. And the screen curve is this theoretical, is for the hydrostatic equilibrium. If you think about it, if the interior of Jupiter is rest, there's no any flow, no any disturbance, it's in a perfect hydrostatic equilibrium, then its coefficients, gravitational coefficients, will be like this green line. But if you take into account all this like zonal flows, all these dynamo motions, then they will produce the distortions, and they will produce this delta Jn. That's the signals of the flows. And because flows are usually small scale and weak, so in the lower order coefficients, the signals is much, much smaller than this background signal, this hydrostatic equilibrium. But in the high order, like n larger than 10, we expect the distortions or perturbations from the flows will exceed the hydrostatic equilibrium. And this is how Juno is going to contribute. And Juno is going to measure these coefficients. And if Juno is able to measure J10 or J12, then this, and even higher, and then these measurements will be mainly contributed from the flows. And so far, before Juno, we only can measure to J6. So it's before Juno, we're impossible to say anything on the interior, especially for all these flows and disturbance. That's why Juno is important. Juno, for the first time, would be able to observe J12 or more. So because of Juno's observations, now we have hope, we have chance to interpret the observations and answer the question what the flows in the interior would be like. But it depends on how good the model is. And this is one calculation from our modeling of the dynamo motions. And we pick up one azimuth of Fourier component of the convective motion, and we do a calculation, see what it will, how much distortions of density and gravity field it will cause. And if Juno measures this number, what Juno is going to measure is this gravity signal. And if it measures any number and any structure, we will do the inverse to get the speed, to recover the flow. Okay, summary. The reality is now we still know little about Jupiter's deep interior. And because we don't have very accurate observations, and we don't have good model either. And Juno probably will greatly refresh and update our knowledge of Jupiter. But if we want to make use of the observations from Juno, and we need a self-consistent and accurate model. And Juno is now producing data, gradually releasing the data. So we are going to intensively involved in the model inverse, and hopefully we can produce some result very soon. And this picture is I took with my camera. This is Jupiter, and it's 4 satellites. Jupiter is very big and bright, so you use the camera is enough. Okay, thanks.
Thank you very much indeed. So we have time for a few questions. Donald. Microphones.
If one thinks of, no, forget that. If one thinks of Jupiter as a great big spinning thing, it's got normal modes. And presumably these are naturally there, and there are a whole lot of normal modes, same as there are in the Earth or in other things, but easier because it's not anisotropic, because it's not a solid. Do people work on the normal modes of Jupiter or not?
I firstly want to say sorry, because that's the first time I'm not familiar with this relevant researchers. I don't quite understand what do you mean by normal modes, and is that the change of the shapes?
So it's the Kelvin modes. So if you kick Jupiter, it will vibrate.
Oh, okay.
Just like a star or the Earth will vibrate with an earthquake.
I see. I don't think it will happen because Jupiter is not like star, and it doesn't have a very, really energetic interior energy source, and it's not going to, not like stars, you have nucleus reactions, produce tremendous amount of energy, and if it has any fluctuations, it will be reflected by the some oscillations of the global oscillations. But Jupiter is not going to do that. Jupiter, from the beginning, at the origin, when it forms a primitive Jupiter, it is much larger than the current size. And because of this the gravitational shrinkage, its evolution, and it's become smaller and smaller, become denser and denser, less compressible. And meanwhile, it's because the conservation of the angular momentum is rotating faster and faster. But all these processes are taking place gradually, and there's no any.
There will nevertheless
fast.
be normal modes. They may not be excited. And what you're saying
Yeah,
is they're
yeah,
not
yeah.
excited.
It's not. They're not excited. I don't think they're excited.
Thank you. Just comment on your question. If you refer to monthly notice, I think in 1994, our friend Douglas Goff got a paper out just in time before the Shoemaker levy impacts, which would have given the planet a jolly good hit. And I think his conclusion was that nothing would have been detectable, but I may be wrong.
Yeah, all right, thank you.
Don't know if I switched that off. Sorry, I'll do it.
Ralph.
If you have two small ones, if you have those internal convection cells, etc., can you pin down the metal content of Jupiter? It's very important for chemical evolution, actually.
I don't think from the internal convections you can.
I mean, if you have a more precise mass model, can you tell how large the nucleus is?
Maybe, I have to say, because compared to Jupiter, its core is too small, and even Juno cannot really measure the signal from the core, and it's too small. And you can incorporate a core into your model of the internal structure, but I don't think you can directly measure the core. Yeah.
What would you need to get its composition?
You mean the composition of the core?
Of
The Jupiter. Okay. If you want to know the composition, because composition, Jupiter is mainly made of like stars, hydrogen, helium. It's a similar composition, but it contains some like ammonia, methane, and other elements, and it will be reflected in the equation of state. Equation of state will enter the equilibrium model. So if you have higher accuracy observations, it's possible to do the inverse problem.
Exactly. So
Yeah,
what would
yeah. You can model the EOS, like you can do the first principle calculation.
But Juno can't do that.
Juno can't do this. Juno is observation. How to interpret the observation? That's your researcher's responsibility. Juno's responsibility. Juno's duty is only to provide you reliable observations. And how much you can get this information out, that depends on how good model you have.
Okay, we must move on, so thank you very much indeed.